Now we're going to look at some problems from chapter 27. So in particular, I have chosen these three, which are 18, 36, and 57. So now let's first start with problem number 18, where the problem basically states the following. So if you want to refer to it, you can go to the book and refer to it later on, but I'm just going to read it out for now. So we're going to do chapter 27, question number 18. So you have a particular figure which is given as the following. So you have two batteries, a resistor connected over here, a resistor connected over here, and another battery that is connected to a resistor like this, and all of this is connected. So you see, you get multiple loops. So this is resistor 1, this is resistor 3, this is resistor 2. You have an EMF directed in this direction, which we call zeta 2, and you have an EMF directed in this direction, which we call zeta 1, and there's a current flowing in this direction through R1, there's a current flowing in this direction through R3, and there's a current flowing in this direction due to through R2. Okay, and you have two nodes in particular, which is at here A and here B. Okay, now the question states that what is the potential difference? Oh, there are another two nodes that I forgot to add, which are at C and D. So C is over here and D is over here. Okay, so now the question states that we need to find the potential difference VD minus VC, which means around this part. So DRC matches a potential difference, and we understand that DRC matches you can either go in this direction through the loop or in this direction through the loop, whichever direction you consider, and we have to find the potential difference between these 2 points D and C. And given are a few information. For example, you know what zeta 1 is, which is EMF 1, which is given as 4 volts, and you know what EMF 2 is, it's given as 1 volt, and R1 equals to R2, which is given as 10 ohms, and R3 is given as 5 ohms. And it's also stated that the battery is ideal, meaning that there is no loss internally from the battery. Okay, so these are all the information that is given to us. So we're going to try and use a couple of equations over here, mainly 3 equations which are given in the book, which is particularly for this. We know we can use the current rule, right, where we know that whatever ingoing current will equal to the outgoing. So over here you see, if we consider at this node over here, from here I1 is incoming, I3 is also incoming, but I2 is outgoing, right? So therefore we can use KCL, meaning current law, and in that case this will be I1 plus I3, which are the ingoing ones, which will equal to I2, which is the outgoing one. Okay, so this is one equation from this circuit. And now if we use the voltage law, meaning we want to do the loop direction now, in that case our first loop, let's consider this to be counterclockwise. So therefore in this direction, in that case we can write the EMFs, or basically the voltages, as to be counterclockwise, so counterclockwise is in this direction, right? So therefore we can write the EMFs in this way. We can start from B and end up in B again, like through the loop. So therefore the first encounter we have over here is zeta 1, and then we come to R1, so which is going to contribute to a potential drop, and therefore this will be minus I1 R1, because you know you have I1 running through R1, and then again you go through the loop, and then you encounter R3, but you see R3's current is in the opposite direction of our loop, so it would contribute to a minus I3, which will counter with the minus already for the resistor, because resistors contribute to potential drops, and therefore we will get plus I3 R3, and then you close the loop at 0. Okay, and this is equation number 2. And then you can do the same with the right hand loop. Over here you take the loop again, we choose to do it counterclockwise, again in this direction. It's just convention. And in that case you can do the same thing counterclockwise from the direction of B, so you go in this direction again. So therefore you will have, first you see you encounter I3, which is in the direction of our loop, so this will be minus I3 R3. And then you go towards and you encounter the second resistor, which is in the direction of our loop as well, so therefore you get minus I2 R2, right? And then finally you see that the EMF is in the opposite direction of our loop, so therefore you get a minus zeta 2, and then you close the loop, and this is your equation 3. So now you have all of these three equations. Next what you're going to do is you're going to solve them, and you're going to solve them simultaneously to configure, because these are algebraic equations, so you're going to solve them simultaneously. From here find out expressions for I1, I3 and I2, and then plug them in your equation 1, which will give you expressions for I1, which is going to be zeta 1 times R2 plus R3. I'm just going to write this directly. If you don't understand the algebra, just let me know. But the way I'm doing this is basically just simultaneously solving these three, and this will be divided by R1 R2 plus R2 R3 plus R1 R3, and I2 will be given as zeta 1 times R3 minus zeta 2 times R1 plus R2 divided by R1 R2 plus R2 R3 plus R1 R3. And finally, since I know I3 given from here is equal to I2 minus I1, I can just use the expressions for I1 and I2 from here and then find out what I3 is. Now, to consider what these currents are equal to, I can of course use these expressions because I already have I1, I have R1, R2, R3, I also have zeta 2 and all of that stuff, so I can just plug them in over here, and finally what you will get is 0.275 amperes for I1, and you will get for I2 0.025 amperes. And since you can use these two expressions, you will get I3 as 0.025 minus 0.275, and this is equal to minus 0.250 amperes. So there's a minus in front of I3, which just means that we might have assumed the direction of I3 wrong. That's all. Okay, but the magnitude is correct. So now what we have to find is basically VD minus VC, right? So therefore you have to find the potential difference between these two nodes, and of course you can find it through various paths. You can go in this direction or you can go in this direction, just finding out the potential difference between D and C. So in that case, one example is you can find from here, let's say I want to find in this direction, I go towards VC. So in that way I can use the loop rule again, and in that case, let's say if I start from point D, this has a potential of VD at point D, and then you move in this direction towards point C, and you see while I'm going towards point C, I encounter this resistor which will contribute to a potential drop, so minus I2 R2, and then I reach point C, which is going to be equal to VC, right? So in that case you can rearrange this equation and you can write VD minus VC equals to I2 R2, where I already know what I2 is and what R2 is. In that case I can write VD minus VC as 0.025, which is I2, times R2, which is 10 ohms, and this will be equal to 0.25 volts. Okay, now you can also take another route, which is in this direction, right, on the other end. So if I go from D to B and then C, I can do that as well, and in that case I will get another expression which is going to be VD if I start from here, and then you see I encounter I3, and it is in the opposite direction of our loop, which is the direction I'm considering. So in that case I will get a plus I3 R3, right, because resistors contribute negatively, but it's in the opposite direction, plus I will get zeta 2, because now zeta 2 is in the direction of our loop towards C, so therefore this will be plus zeta 2 and it will equal to Vc, which is our ending point at C over here. So in that case, again, I can rearrange this. I can write Vd minus Vc equals to, so Vd minus Vc will just equal to minus I3 R3 minus zeta 2. In that case, what you will get finally is you will get minus of minus 0.250, which is I3 times 5 ohms, which is R3 minus 1 volt, which is zeta 2, and therefore you will see that you will get the same expression as 0.25 volts from here. And that solves our problem because that is what we were asked by the question. Okay, now let's move on to problem number 36, where the problem states so you have 36, right? Okay, so 36 is the big one. Now from 36 you have a circuit which looks like the following. So let me draw the circuit down first. So you have a resistor, you have a battery, and then you have another resistor connected in this way, and you have another resistor connected in this way, and then you have this, which is again connected to the ground, so this is earthed. Okay, so this is your this is your circuit. Now you have an initial EMF in this direction, let's call that zeta 1. This is R2, this is denoted as node A. This is R3, this is R1, and this is zeta 2, which is in the direction of upwards, the EMF. Okay, so now this is what you have as your circuit. Now the question is, you are given a couple of values for the EMFs. For example, EMF 1 is 6 volts, EMF 2 is 12 volts, R1 is 100 ohms, R2 is 200 ohms, and then R3 is 300 ohms. So you're given all the values. And now there's a couple of questions. So you have A, B, C, D, E, and F, and G. So therefore the question is a bit big. So of course it's going to take some time to solve this. But now what the question states is, you can refer to the book as well. It states that one point of the circuit is grounded. So this point is the circuit is grounded, and we understand that when the circuit is grounded, it basically takes away all the potential and earths it, right? So at this point V will equal to 0. Okay, so now the question is, what are A, the size and direction of the current through resistance 1? So A and B want the size and direction up or down of the current through resistance 1. তার মানে হচ্ছে resistance 1 এর থ্রুতে কি কারেন্ট ফ্লো করতেছে সেটা আমার জানতে হবে। I need to know the magnitude, which is the size of the current, and also which direction is our I1 following through. Okay, so now let's look at how to solve this. So first of all, what we're going to do is we're going to use the junction rule, and since this is a multi-loop circuit, right, we're going to use the junction rule like this. We're going to consider first the left hand side loop, which is going to be in this direction, right? So let's first assume, because আমরা assume না করলে আসলে আমরা direction গুলো বুঝতে পারবো না. In that case, let's assume that all the currents are in the direction of our loop, okay, which is here. So let's call this I2, let's call this I1. Okay, so we're considering that the currents are flowing in the loop directions. Okay, so now if this is true, and we're going to also consider that we need the direction of I3 as well. So let's say that I3 is in this direction, which we're going to take in the direction of the loop later on. But we will see that if indeed we get, you know, a different direction of the current, it will just give us a minus. So it's okay if we are assuming something at first. Okay, so now considering that the currents are in this direction, I can write I1, which is the outgoing current over here from node A, as equal to I2 plus I3, because I2 and I3 are ingoing, right, through the loop. So therefore that will help us consider this leftward loop first. So this is equation 1. So now first let's consider this left hand loop. So we know, of course, zeta 1 is in the direction of the loop, and therefore I2 is also in the direction, so it will contribute to an I2 R2 with a negative, and I will have I1 R1, which is also in the direction of the loop, so a negative as well. However, since I know I1 is equal to I2 plus I3, I can just write this as I2 plus I3 R1 equals to 0. Okay, this is the first loop, so equation 2. Now the second loop, again, I can use this, and since I'm taking the loop in the direction of EMF2, so this is going to be EMF2 minus, you see I3 is in the direction of the loop, so I3 R3, and then again you come around and you have I1 again in the direction of the loop, so therefore this will be an I1 R1, except I can now write I1 again as I2 plus I3 R1, and this will close the loop as such. Okay, so now by plugging in on the all the values that I have over here, I can figure out what my I1, I2 and all of that is. And now remember that the question asks me to figure out I1. Basically part A tells me what is the current through R1, and it asks me to find the size and the direction, right? So if I plug all of this in, you will see, solving, you get I2 as 0.0109, which is positive, and therefore it is exactly the direction that we assumed earlier. So I2 over here is rightward, যেটা আমরা হচ্ছে ধরে নিছি আগে থেকে, so this is correct because you get a positive answer. Okay, and I3 also, you will see that you will get 0.0273, which is leftward, because you see this is exactly, since we get a positive answer, it is correct in assuming that this is going to be in this direction. So this is also going to be leftward. And finally I can find I1 as I2 plus I3, which is just going to be 0.0382, which is also positive. Therefore we are right in assuming that I1 will be downward. Okay, and this is your answer for part A and part B. So moving on to the next part of the question. The question asks part C and D as the size and direction of the current through resistance 2. So আমরা এটা already বের করে ফেলছি. So part C and D asks you to find the size and the direction of the current through resistance 2, which is I2 over here. So basically this is the answer to part C and D. Okay, now next question is E, the size and direction of the current through resistance 3, which is also something that we found as I3 over here. So this is the answer to E and F. And now finally we have to go to part G, where the question asks us to find the electric potential at point A. So we need to find the electric potential over here. Okay, so now basically what we need to do is we need to find VA, right, which is essentially the potential over here. So I understand that the voltage VA will just be, you know, the potential over here, as in if you want to find VA over here, you can go through the loop again, which is something that we did earlier, and basically this part over here will as in, if you want to look at it in this way, this divides your potential between this node over here in the circuit, this node over here in the circuit, and this node over here in the circuit. So basically I can take VA as this, where let's say this is some, okay, let me do this part and denote this as B. So if I want VA, I can just consider these two nodes, and I can take the potential difference between these two nodes, and it should give me what VA is. Basically what I can do is I can take this circuit and I can write VA through over here, and I will encounter minus I1 R1 and come to VB. Okay, so basically I'm taking the potential difference between A and B, but I already know that this part is grounded, right? So therefore VB is essentially 0. So in that case, if VB is 0, then I can write VA as just I1 R1, which is essentially the voltage across R1, right? So in that case, I can write G now as being VA equals to I1 R1, which is basically I1, which I got as 0.0382 times R1, which I know as 100 ohms, given as here, and this will equal to 3.82 volts. That is the voltage, the potential at point A. And that solves our problem, which was problem number 36. Now let's move on to the next one, which is problem number 57. So problem number 57, let's take that out from the book. So problem number 57 is from RC Circuits, and you have the circuit again. Let me draw it out as the following. So you have a switch, you have a resistor, you have a capacitor, and then this is connected to a battery. Okay, and this is the resistor, this is the capacitor, this is the switch, and the EMF direction is in this direction, obviously, and this is your circuit. Okay, so the question asks that you have the switch in this figure and it is closed at time t equals to 0. So at t equals to 0, switch is closed, which basically means that you are now letting the circuit run, and therefore if you let the circuit run, the capacitor, since it's connected to a battery, will start charging, right? So একটা uncharged capacitor at t equals to 0 begins charging, and you can understand from the equation, from the question, that you're given an initial capacitance of the capacitor as 15 μF, which means 15 microfarad, and through a resistor of resistance R that is also given in the question, where this resistance is basically 20 ohms. And the question is, at what time is the potential across the capacitor equal to that across the resistor? So I need to find out এখানে through the G potential, এটা through the key potential, সেটা কখন equal হবে. Okay, so basically I need to do this. I need to equate VR, which is the potential across R, to VC. Okay, and that is how I can solve this equation. Basically equate it and then find at which time these two are actually equal. So now what we're going to do is we're going to simply use the equations that we had earlier when we were doing RC circuits, so which was in particular these two. So basically VR এর জন্য আমরা already জানি, মানে whatever voltage is running through the resistor R through Ohm's law, I know that this is IR because V equals to IR, right? And I flows in this direction, so I have IR over here, and VC is just the voltage across the capacitor. So let me write it as V cap. Okay, and we have to equate these two, meaning we have to write IR equals to V cap for us to solve the equation. Okay, so now first of all I need to figure out what IR is and what V cap is. So I can just use the expressions that I have from the book, right, that we solved in the earlier video. So now প্রথমে আমরা এটা করি. So this is equal to IR, and I know I as dq by dt, right? And I already have an expression for this when I'm charging the capacitor, which I wrote earlier as zeta by R times e to the power of minus t by RC. So I can just plug this in over here. So dq by dt times R, so this is times R for this expression, right? And therefore this just cancels the R over here, and I have zeta e to the power of minus t by RC. Zeta is just the voltage, so I can just write this as the total voltage, e to the power of minus t by RC. So this is your expression for IR. The next thing that we have to do is find this voltage. Basically this is the voltage through the capacitor, and I know that this is just going to be, you know, what we found earlier as well. We can just use that formula, which you see we found VC from the book, if you remember. It was given as Q by C, which is equal to zeta times 1 minus e to the power of minus t by RC, right? So the EMF is basically the total voltage, and I can write this as 1 minus e to the power of minus t by RC. And this is your expression for V cap. So now what I do next is I equate the two, and equating the two will just give me an expression of V times e to the power of minus t by RC, which is equal to V times 1 minus e to the power of minus t by RC. And I simultaneously solve this, where you can just, you know, do the algebra. Let me do this. This is V minus V times e to the power of minus t by RC. So you get two expressions that are the same over here. So you take that to this side, you get 2V e to the power of minus t by RC equals to V. Okay, or I can just do minus V equals to 0, and then you take V common. So you get 2 e to the power of minus t by RC minus 1 equal to 0. And therefore V is gone, so you get 2 e to the power of minus t by RC minus 1 equals to 0, 2 e to the power of minus t by RC equals to 1, and therefore the exponential is the following. So I can write this as half, and therefore I can take a logarithm on both sides, and this will be minus t by RC equals to ln of half, or I can write this as minus t by RC of logarithm of 2 inverse, which would just give me a minus up front. So minus t by RC equal to minus ln 2. That gets rid of the minuses, and therefore t equals to ln, or I can write this as RC ln 2. Okay, so now you know your expressions for R, which is given in the question as 20 ohms. And you also know your capacitance, which is given as 15 microfarad. You just plug that in over here, and you get T as 0.208 into 10 to the power of minus 3 seconds. And that is exactly the time when the voltage across the resistor and the voltage across the capacitor is equal. And that solves our problem. So the three problems we solved were 57, 36, and 18. So this should more or less cover the ideas and concepts covered in chapter 27. But if you have any other questions, you can of course reach out to me and ask me whatever you have confusion about.